All right, ladies and gentlemen, in this video, I'm going to talk about the relationship between work and energy. And I think if you watch the video, the latest video, it kind of like gives you a hint that really when you do work, you change your energy level. And I use the example, you can go back to the old video, I use the example of something going on a ramp, right? And I showed you, if you remember, that the work done by the applied force, okay, was really mgh plus 1/2 mv square v final square minus 1/2 mv initial square. So you can see that this is a change in your gravitational potential energy, and this is a change in your kinetic energy. And then you can include even the spring, right? So I think we can write that the work is really something that changes your energy level. You can either increase it or decrease it. Okay, so that's done in the previous video. Now, if you also watch the previous video, I showed you that the net work is only the change in kinetic energy. Okay, now this work here, done by the applied force basically, is the change in total energy here. And here we're talking about mechanical energy. Mechanical energy means, and that can apply to other forms of energy. Mechanical energy means like we're talking about spring potential energy or elastic potential energy. We're talking about gravitational potential energy, and we're talking about kinetic energy. But this rule applies to pretty much everything, even chemistry, right? When you do work, you change the energy level of something. Okay. Now, instead of writing W equals change in energy, now change in energy is energy final minus energy initial. Now, it's very rare that you're going to see me writing it like this, okay? Even though your formula sheet shows it like that, I'm going to always write it like this here. And I'll tell you why. This makes more sense to me in the sense that, well, I do have some energy, right? Some work is going to be done, right, on the system, right? And I will define system in a minute. So my energy level has to change. It will either go down or go up. Okay. The net work done on an object is equal to the change in kinetic energy. Now, I showed you, I just wrote that earlier. And you can go back to the previous video to see it. Now, let's see if we can answer this question here. Actually, you know what? I'm going to let you answer that in class, right? But for now, I'm going to talk about this concept of systems. And if you can see that everything that comes after here is all RTs, and it's just like a bunch of pictures we have to analyze. Now, what do I mean by system? Maybe I should use an example here. Okay. And I have a couple more examples towards the end. Now, I'm going to add to what's in this picture. This is page 12, pages 12 through 14. Let me just make sure I'm not missing anything. Yeah. Okay. Now, the definition of the system, right, will change the way the equation is written. Okay. So this E initial plus work, and this work here is done by external forces outside of the system. Now, external work depends on how you define your system, equals energy later, final energy, right? Now, in this example here, we circled or we dotted around the person and the earth, which means earth is part of the system, which means earth does not do any work on the girl. So we have to make sure we understand that. Okay? Now, the girl inside this system here is going to have, because earth is included, is going to have some gravitational potential energy, okay, because she's above this point here, which is the zero potential energy reference point. So in here, what we're going to do is that we're going to say, well, the girl has gravitational potential energy. The Earth is part of the whole system, right? So basically, there is no work being done by the Earth, that's the planet Earth, equals the energy later. Well, later she's down to this level here, right? Which means she has no gravitational potential energy, okay? Because she's right at the reference. And the only thing that's happening here is that she's moving. Now, this is a frictionless surface, right? Assuming that it's a frictionless surface. Now, basically, gravitational potential energy now is equal to kinetic energy. Now, if we have to draw this in an energy bar chart, and this is what we have here with the equal sign, this is the initial condition, this is the final. So let's take a look at it. Well, the energy that she has here, she's not moving, she's starting from rest, right? That's why you see nothing here. And then all of her energy is in the form of gravitational potential energy. Now we look at the final state. And at the final state, she's at the reference level, she has nothing, no gravitational potential energy, and all her energy is converted to kinetic energy. You see how these two bars are equal. Now, let's add to this. Well, let's just say that there is friction here, okay? So if there is friction, there is work done by friction. Now, that's going to be negative work. Now, even though the slide is inside this dotted line, friction is still an external agent, okay? Work done by friction equals the kinetic energy at the bottom, right? Now, you can see clearly here that because of friction, the kinetic energy at the end is going to be less. So this is how we draw our chart. So it would be K, U, G, this is all initial, maybe some work done by external agents. Now this is before the bottom. Now, and then you have your K final, is your gravitational potential energy final, and that's that. Okay, let's see what happens here. Well, we start with no kinetic energy, so we have nothing here. She has gravitational potential energy, so let's just say she has, I don't know, 3 bars, right? And friction does some work. Now, the work that's going to be done by friction is going to be negative. And why is that? Because you're moving down, friction is opposing you, so there is that 180 angle between the two. So the work done by the external force, let's just say I'm going to put 1 bar here, right? Now, according to this equation, the sum of these two, right, has to equal to the sum of these two at the end. Well, I know at the end, she's right at the reference. So she has no gravitational potential energy at the bottom. So how much kinetic energy does she have? Well, she has the sum of these two, which is really a difference. So she has 2 bars. Okay? Now let's keep adding to this. Let's say when she's at the top, someone gives her a push, which means she has an initial velocity. So let's see how that's going to change here. Well, when she's at the top now, she has some kinetic energy initial, so I'm going to put a subscript here. Okay? And what's going to change? I'm going to have to give her some kinetic energy here. So maybe I'll give her 1 bar of kinetic energy. Right? So now when she's here, the sum of all this here has to equal to the sum on the other side. So now, so she's going to have 3 bars. Okay, I hope this makes some sense, right? Now we can keep adding to this. Let's just say, let's just try to figure this out when she's maybe halfway here, right? Halfway the height, okay? Same thing as halfway down that way. So let's see what this is going to look like. So I'm going to make this my final state, okay? Now, there is kinetic energy, because I'm giving her a push. There's some gravitational potential energy. There is friction, but it's going to be less than going all the way down to there. I think you guys can see that. The work done by friction is just half, because I'm taking half of this, right? The force of friction is constant, but the displacement is different. Now, when I'm at this level here, I do have two forms of energy. I have the potential energy, gravitational, final. Now I call this my final state, plus some kinetic energy. So you can play with this in a lot of different ways. So now when you draw in your chart, well, it's starting with some kinetic energy. So I'll just make that 1 bar, right? I'll make this 3 bars. And this is not drawn to scale, by the way. There's some friction, so I don't know. Maybe I'll put like a bar here. Or I can make these 2 bars. It doesn't really matter, right? Give it a big push. Now, when she's at that level, the gravitational potential energy is going to be just half of that, basically, right? So I don't feel like having fractions here. So I'm going to make this 4. So she's going to have half the potential energy she started with, okay, because it's half the height. 1, 2. And let's just do the addition here, right? So basically these 2, 4, 5, 6 minus 1, so that's 5. So now I have 2 here. I have to have 3 in here. Otherwise, the equation would not make sense. Okay, so I hope we get this. Now, let's change our system and look at this differently, right? Well, what happens if our system is just the girl? The Earth is not included. Okay, so now I'm going to write my equation again. Energy initial plus work done by external agents equals energy final. Okay. Now, this girl has no energy at that level. And the reason for that, because Earth is not included in our system, right? So she has no potential energy. She has no kinetic energy. You're only going to have potential energy if the Earth is part of your system. If the Earth is not part of your system, it becomes an external agent, and you will have to do some work on you. The force of gravity will do work. Again, I'm going to end up with the same equation. It just things will be written in the different places. Okay, so now I'm going to write Ki plus Ugi. So just to show you what I mean. Now the work, I'm going to assume that it's frictionless. So the work done by gravity in this case, right, equals K final plus Ug final. Well, let's see. Now, let's just start with not moving. Because the Earth is not part of the system, she has no gravitational potential energy. It's extremely important we understand that. Okay. Now, the work done by gravity is just going to be mgh, right? Well, mgh was also the gravitational potential energy when the Earth was part of the system. See what happened here? I just moved this around depending on what my system is. When my system included the Earth, there was no external work done. Okay? When my system excludes the Earth, now the Earth becomes an external agent that does some work on the girl. Okay. Equals she's going to have kinetic energy at the end, right? But we cannot even talk about the idea of gravitational potential energy. I know that it's 0 if Earth is included, but here we cannot even talk about it. It's like it's 0 because Earth is not even part of the system. So this notion of gravitational potential energy is not even there. Okay, let's see what happens if there is friction all the way down. So my equation will look something like this. Well, the work is done by 2 things. It's done by Earth and it's done by friction. That's equal to K final plus Ug final plus, that's it, okay? So this here don't even exist, okay? Because the Earth is not part of the system. Now, all we have is the work done by gravity, the work done by friction, right? And the kinetic energy at the end. So let's see if we can draw a chart. Oops. Well, this is nothing. Cannot even talk about this concept. The work done by gravity has to be positive. So let's make it 3 bars. Work done by friction is negative, so let's just give it 1 bar. Now, the combination of these 2 should give me my kinetic energy later. So that's 2 bars. Okay? All right. Again, if we give the girdle a push, the only thing that's going to change is this is going to become something. It's going to have a bar or 2 bars, whatever. Depends on how hard you push her. So that's pretty much the energy bar charts. All right, so let's look at the next one, and we make some changes here. Okay, I'm going to treat this differently than what's just on here. So I'm going to look at different systems here. So I'm looking at the car driving on the road. Okay, and I'm going to consider the Earth as being part of my system, right? Okay, so here I'm going to say, well, the initial energy plus any work done equals the final energy. Okay, so if the Earth is excluded, right, or included, I'm sorry, then I will be dealing possibly with the gravitational potential energy, with the initial kinetic energy, maybe some work done by some external agents, and I'm going to see what's happening to my mechanical energy later. Okay. Now, this is 0. This exists because Earth is part of the system. Well, this is 0 because I'm still at the ground level, right? The car has some kinetic energy, okay? But it comes to a stop, right? So which means its kinetic energy at the end is 0. So I end up with no energy at the end. Okay, so the work is got to be done by friction, right? Equals 0. So now if I draw my chart, well, let's say it started with 1, 2, 4 bars. Friction has to be 4 bars. 1, 2, 3, 4. And then what do I end up with at the end? Nada, nothing. Okay? Now, if you read this, it says K changes to the internal and increases the internal energy of the system. And the reason for that is because the tires will get warm and stuff like that. So there is some change in the internal energy of the system by just heating up the tires. Okay? There's a lot of ways you can change the internal energy of a system. Now let's try this with Earth as not part of the system. So if Earth is not part of the system, this term should not even be mentioned. Okay, and it would look exactly the same. Okay. Now let's look at the one under it. Okay, I'm going to look at the Earth as part of the system now, right? Okay. All right, so the energy initial, I think you got that, so I'm not going to write that. So I'm going to talk about all the different kinds of energy that I have. So gravitational potential energy plus, now there is a spring involved. So maybe it's something stored in the spring plus kinetic energy initial plus maybe some work done by external agents equals gravitational potential energy later, the sum of the mechanical energies later, basically. Okay. Now, let's see what happens here. Do I have gravitational potential energy here? No, I'm looking at this as the reference. Good, so that's gone. Okay. Is there energy stored in the spring? You better believe it, because the spring is compressed. Is there kinetic energy in the beginning? No. The toy is not moving in the beginning, so that's 0. Now, is there any work done by outside forces? Now, if we ignore air resistance, if we had air resistance, we'll have to include that in there. That's kind of like a form of friction. Okay, so there's nothing here. And is the toy above where it started? Absolutely. So there is some gravitational potential energy. Is the spring compressed or stressed or stretched? Not really. Okay, and is there kinetic energy? Well, if it goes to the highest point, no, there isn't. It has to stop and come back. So we're looking at that moment when it's at the highest point. So if I draw my chart, well, it's already here, right? So the only two things you see is the energy in the spring turns into gravitational potential energy. That has to do with height, with position. Now let's change a couple things here. Let's say Earth is not part of the system, so I'm just going to concentrate on the toy by itself, right? So this notion of gravitational potential energy is no longer there, so we're going to have to drop it, right? So the only thing I'm going to talk about is, well, is there kinetic energy? Maybe, we'll see. Is there energy stored in the spring? Oh, we'll see. Plus work done by external agents, okay, equals kinetic energy final plus energy stored in the spring final. Okay. Well, yeah, there's no kinetic energy in the beginning. There's definitely something stored in the spring. There's no external force, right? And there's no kinetic energy. So it looks exactly like that, right? Now let's just say, in here what I said, the toy and the spring are together. Sorry. Now I'm going to change my system. And I'm only going to look at the toy without the spring. Spring is no longer in the system, and Earth is no longer in the system. Okay? I'm sorry, for the previous one, I think I took the Earth out of the system. Let me correct that. I'm taking the Earth out of the system, so I cannot talk about the, what do you call it? The gravitational potential energy. But there is definitely work done by gravity. Yeah. I forgot that I took the Earth out of the system. Okay? So there's definitely work done by gravity. And the work done by gravity is going to be negative, right? So here we got nothing, nothing. It's going to look exactly like the other equation, because the work done by gravity here will be negative mgh. If you move it to the other side, it becomes mgh. Okay. Now let's just concentrate on the spring only, right? And see what happens. Well, we're going to say kinetic energy plus maybe something in the spring plus, we're going to concentrate on the toy only. I think I said spring. We're going to concentrate on the toy only. Sorry. I'm trying to go fast to beat the bell. Plus work done by any external agents, and I don't know what they could be, equals kinetic energy final plus energy in the spring final, and that's it. All right, so this is not moving. So again, the only thing we're looking at is just the toy. No spring, no Earth. Now, the spring is not in the system, so we cannot even talk about this concept of energy in the spring. But the spring is going to do some work, right, on the toy, because the spring is external to our system. So the spring is doing some work, and the work that it's going to do is that 1/2 k x squared, right? Because all the energy sitting in the spring is going to do work on the toy. Gravity will also do some work, except the gravity will do negative work. You're moving up, gravity is pulling you down. Minus mgh equals, now this is 0, and spring is not even part of the system, right? So we cannot even talk about that. That shouldn't even be there. And this is 0 at the end. Now if you manipulate this, you get what we started with. So again, it's the same equations, except the terms are in different places depending on what you choose as your system. All right, I'm out. Peace.